This video shows three different motions that are different and yet very similar. The pendulum on top, the cart being pulled back and forth by springs, and then the object moving around on a turntable. They all make the same number of oscillations per second, or another way of thinking about it is that they take the same amount of time to make just one oscillation. These ideas are called frequency and period, and they are the way that we describe the rate at which something oscillates. Frequency is just the inverse or the reciprocal of the period. We'll find that all of these motions can be described by this equation, x equals x maximum times the cosine of omega t plus phi. And this function is an indication of something called simple harmonic motion, or SHM. So what all the parts of this formula refer to? So x and t, I'm going to assume that we know what those mean. X is your position, your displacement. Time is a running clock that's going on. Not the time, not the period, but just time in general. So x max is the maximum displacement of the object compared to that central or that equilibrium point. It's also called the amplitude, and sometimes you see it referred to as a capital A. I think that's usually what a math class uses. It's always a positive value. It's just sort of how far from equilibrium, whether it's in the positive or the negative direction, and it's set by the initial conditions of the motion. And so usually what we'll do is we'll give something a push, or we'll pull a pendulum back and let it go. And that initial motion determines the amplitude. The other parts of this, one of them is called the phase constant. The phase constant is given a symbol of phi, and it's something that we won't actually use very often. We have kind of a way around it that I'll explain in a minute. But it describes, again, the initial conditions of this motion. But very often what we'll do is, rather than using a phase constant, we'll instead choose to use the sine function instead of the cosine, or include a negative sign, or negative or positive sign to indicate what's going on. But this last part, this omega, is very important. This is called angular frequency when we're talking about motion oscillations like this, as opposed to angular velocity when we were definitely talking about a circular motion. It is a value that is related to F and T, F and capital T period, but it is adjusted from those values so that it's in radians per second. That helps with the sines and cosine functions to make sure that the units are all correct. This formula here is also something that's available on your formula sheet. It shows all the mathematical relationships between period, omega, that angular frequency, and F, the regular frequency. All right, so where does that cosine come in? What all these symbols mean? Well, let's imagine that we have a mass hanging in a spring. This is kind of our typical example, one of the reasons why we've been studying springs. And let's imagine that we lift that spring up above its regular balance point, its equilibrium point, and we let it go. That distance that is marked with a red arrow, that would then determine the amplitude of the motion. That represents the maximum displacement of the object compared to the equilibrium point. We'll see later how that determines the kind of the extent of the motion, but it doesn't determine the rate of the oscillation. The terms like T, F, and omega are not determined by that amplitude. But hopefully you can sort of see how, as that object is sort of bouncing up and down, you can almost imagine that cosine curve being overlaid. The object is traveling at its fastest as it goes through the middle, and it slows down to a stop at the top and the bottom. And so there is a curve here. It's not just a straight line bouncing back and forth. There's a gradual change to its motion as it goes through. And it does turn out to be a cosine function. We'll talk later how that's shown. But you can see how that amplitude, again, is above and below. Amplitude is, again, always a positive value. Whether it's above or below, it's just talking about how far, to what extent the object oscillates. Now, the omega you can't quite see within the motion, but if we were to time how long it takes to go from this point to this point, to go up and then come back down again, that would be capital T. That's the period. Or if we were to say to watch this for a certain amount of time and divide the number of oscillations by the time, that would give us the regular frequency f. And if we take 2 pi times that f, or if we take 2 pi and we divide by that period, that gives us this thing called omega. And it times the time tells us at what stage or phase the object is in within this oscillation. So it helps match it up with the cycle of the cosine graph. So in the previous problem, we sort of set the stage by taking the object and lifting it up. And so the initial position of the object was here, just like a cosine graph would be. That means that the phase constant, or the phase angle, would be 0. We wouldn't have to have that phi symbol within the function. And so that simplifies things. So we could just write a times the cosine of omega t, or if you prefer, x max cosine omega t. Again, either one of those is acceptable for amplitude. But if instead we pulled the object down, we could introduce a phase constant. But instead, what we could do is just switch to a negative cosine graph. Just flip the graph over. And so rather than always thinking about that value of phi, this is another way of approaching a problem. Or if maybe our object was started at the equilibrium point and we just gave it an upward push, then that would correspond to this third graph, and that is a sine curve. Okay, so we could just, again, switch to the same sort of basic look of the function, but use the sine function instead. And of course, the last one here is the reciprocal of that, the flip of the sine function. So we could just put a negative sign in front. So what I want to show you is that usually that phase constant is not necessary. In most situations, we can just work from here. The next video talks about how the position and the velocity and the acceleration all relate to each other within the simple harmonic motion.